the mean of a discrete random variable. Our objective, we want to compute and interpret the mean of a discrete random variable. Let's remind ourselves what we know. We know what a discrete random variable is, a random variable that has either a finite or a countable number of values. And we know what the mean is. The mean is one way to represent a data set's center. It's the one number all the numbers would be if they were all the same. All right, to calculate the mean of a discrete random variable, we're going to multiply each value of the random variable by its probability, and then we're going to add these products. Give me a second here. Okay, so here is that in mathematical symbols. We're looking at a population mean here because it's mu sub x, is equal to the sum of, let's add all these products, the sum of all the products of the value times its probability. So that math symbol is there. We'll take a look at an example and we'll show you how that looks. All right, an example. In the Sullivan's Statistics Survey 1, individuals were asked to disclose the number of televisions in their household. In the following probability distribution, located in StatCrunch 6-1-17, the random variable x represents the number of televisions in households. Here's what they came up with. Okay, the probability of having 0 televisions is 0. So it appears everyone had at least one television, and no surprise. The probability of having 1 television, 0.161 as a percent, about 16%. The probability of having 2 televisions, 0.261, etc. And they got up to 9, a whole lot of televisions. So what is the mean of the random variable x? Before we go to StatCrunch, let's take a look at how we would do this by hand algebraically. Okay, whoops, let me come down and we can see that. All right, so mu sub x is equal to, well, we multiply every x by its probability. So we would take 0 televisions and multiply it by its probability 0. And we would add, and we're going to go do the same thing for all 10 of these multiplication problems. We're going to add them all together. So plus 1 television, the probability 161, plus 2 televisions times 0.261, etc., etc., etc. 3, 4, 5, all the way to 9 televisions times its probability, which is 0.01. Once we do all of that by hand, we'll come up with 3.21. So the mean number of television sets is a little over 3 television sets. Let's take a look at this in StatCrunch. We're using Stat Calculator's Custom. So I'll pull StatCrunch in here for us, and I think I got that lined up for you. Okay, so we're in chapter 6, so we'll go to 6_1_17, there it is. And here is our data set. Number of televisions in this column, the probability in this column, just like we saw. Looks like I'm a little bit, maybe that's a little clearer. Good. Okay, so we're going to go to Stat, and we're going to go to Calculators, which is right here, and Custom is at the bottom down here. I'm going to select Custom. Okay, my values, this asks us for where are your values and where are the weights. Well, the weights is the probabilities. So the values is the TVs, 0 televisions, 1 television, 2 televisions, 3 televisions, etc. The weights, what's the probability? That's the weights, that's the probability. And then we'll compute that. And it gave us the distribution. As we scroll down, right down here, we see we have the mean and the mean is 3.21 right down there. So that's how it's done with the technology. Okay, let me come back to our notes and our lesson. Going to turn the paper over. How do we interpret the mean? Okay, the mean in these situations is interpreted as follows. I think I got that straight. Okay. The mean of a discrete random variable can be thought of as the mean outcome of the probability experiment if we repeated the experiment many, many times. So if we take a group and we come up with a mean and we do that over and over and over many, many times, in the previous example, if we repeated the experiment many times, we would expect the average number of televisions to be 3.21. Okay? Note the word expect, because what that says to us is down here in my box, because the mean of a random variable represents what we would expect to happen in the long run. It's also called the expected value, which is represented by E of X, the expected value. What do we expect is going to happen over the long run? Okay, well, we expect over the long run that we're going to find that the average number of televisions is going to be about a little over 3 per household. Over the long run, the expected value. Okay, that comes into play in both business as well as probability games, going to Las Vegas, etc. And they can often use this to make predictions, to talk about to figure out what they expect to happen. So here's an example where you can see that, kind of a real life example. A term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. Okay? These policies have premiums that must be paid annually. Suppose an 18-year-old buys a $250,000 one-year term life insurance policy for $350. According to the National Vital Statistics Report, the probability that this 18-year-old male will survive that year is almost 100%. 0.998937, 99.837%. As you might imagine, the vast majority of 18-year-olds are going to live to see 19. Okay, it's not an old age. Not many people are dying at 18. Compute and interpret the expected value, the long run value of this policy to the insurance company. Okay, what does this mean to the insurance company? Obviously, they have money coming in, $350, but if the 18-year-old dies, they have a whole lot of money going out, $250,000. So what's happening over the long term? Are they making money or are they losing money? What is their expected value? So I'm going to create kind of an outcome table. So the outcome. All right, the outcome is the 18-year-old is either going to live or the 18-year-old is going to die. Okay, over that 1 year time, this 18-year-old male will live or die. Okay, now for the insurance company is going to have a gain or a loss. So this is what they're calculating. Okay, a gain or a loss. Now, they're playing. The insurance company wants to be making money. They don't want to pay out more than they take in. Well, if the 18-year-old lives, the insurance company collected $350, so plus $350. The insurance company is up $350. Okay, they paid out nothing. You lived, you gave us $350 for a 1 year insurance policy. If you died, we would have paid out $250,000, I guess, to your family or to whomever you said, but you didn't die, so we earned $350. Okay? If the 18-year-old male had died, the insurance company would lose a negative $250,000. That's quite a big loss. Okay, but they've used tables to come up with these numbers, and they feel fairly certain that there won't be too many 18-year-old males that will die between 18 and 19. Okay, now what's the probability? So the third part of this probability table is the probability. Okay, the probability of living, the probability the male will survive is 0.99. I'll put a 0 in front. 998937, which we know, because it's right here, is 99+%. Okay, that's a really good chance you're going to be living. What's the probability that you die? Well, it's 1 minus the probability that you live. So it's 1 minus 0.998937, which is equal to 0.001063. Because your probabilities, of course, have to add up to 1. You're either going to live or you're going to die. There's no middle ground. There's no additional choice. So these two probabilities must add up to 1. So like we did before, we're going to multiply this times this and add it to this times this. And we'll get the expected value. So the expected value E, let me go up a little bit so we can see that it's just a little bit clearer, is equal to positive 350 times its probability, 998937, plus this number, which is a negative 250,000, times its probability, which is very, very small, less than, wow, just barely above 1/10 of 1%. Okay, so in the long run, what's going to happen with this money? This goes into a calculator. In the long run, we have a positive $84.25. Okay, so what is that? Let's interpret this. Okay, up here it says, let me get this out here, compute and interpret. We've computed it. In the long run, I want to show this. In the long run, the insurance company is going to be making money. That's the positive. We're looking at this from the insurance company's perspective. The insurance company, for every single student who buys this policy, the insurance company will be making $84.25 in the long run. Every policy will be worth to them $84.25. Is that how much they want to make per policy? Is that a good deal for them? Are other insurance companies making more, making less? Where do they stand? I don't know. But in this situation, for this insurance company, they're making money. They obviously don't want to be losing money because they can't pay out if they're losing money. So let's write that down. Insurance company. I hope you can see this. Let's double check. Yep. Expected, this is expected value. Expected to make, that's the positive, on average, $84.25 per policy. Okay, in the long run. Expected value is about long run outcomes. There you go. So there's an example of a real life use of the long-term mean, which can be called the expected value in a business situation.